Welcome to the last live lecture, if not the last lecture overall, of quantum physics for non-physicists. So this is lecture 28, and today is the 17th of December. And today we'll continue with spin. So we'll talk about generalized spin and continue on how to add systems with different spin. And we'll start talking about angular momentum. We'll see how far we get into this. And our daily analogy has to do with things that you in practice only do once. So for example, chocolates, they're very, very easy to buy, already made, like little bonbons or pralines, and they're delicious, but you might once think like we did over here, oh, why don't we make it by ourselves? So we get all this stuff, all these gadgets like the little machine to keep the chocolate hot, and the little molds for chocolate, etc. And it takes several hours to make them. And they're delicious, and you're very happy that you made them, but this is so much work that next time you'll just buy them yourselves, right? Will we ever use them again? I don't know. Similarly, today we'll do a few things that we only do kind of once in our lives, and then we just buy them ready-made. So one will be to calculate some coefficients that are important for this adding spin problem. The other one, which you might not do today, but in the next lecture, will be to compute like the spherical harmonics. These are just the eigenstates of spin when spin is about rotations like angular momentum. And the last one finally is to do the hydrogen atom, which is a very important thing. Like it was the first time that we could see like this new formalism of quantum mechanics actually explain like all the behavior of a very concrete physical system, like the first atom, the most simple atom that there is. So it's historical, very important. It's nice to be able to do it yourself. In practice, you do it once now and then you'll never touch it again. Right? Even if you work in quantum physics, even if you work in atomic physics, it's very rare to do these things by hand. We have some housekeeping to do, so I'll talk about the exam and the missing lecture time. So let's start with the exam. As you probably know by now, it will be on Friday, the 19th of February at 10:30, and it lasts 2 hours. They can take this a cheat sheet, which should be 2 pages, so one sheet, double-sided, A4. I don't care if it's 2 like independent pages or the same. Please don't write me asking this. It should be handwritten. Again, if you want to write it on a tablet and print it, that's fine. Just don't appear like several of you with the same one. That would not be nice. We will have a mock exam available by the end of the first week of January. This will be an exam that has the same structure and kind of the same topics. Of course, the actual exam will be a bit different than this, but it will have the right structure. This is because it's the first time we're teaching this lecture. So next year, the mock exam will be the exam from this year, for example. So I will also publish like a detailed list of topics that can be in the exam. This will follow more or less a lecture, but there are some things that I might say, oh, this was too hard, this will not be in the exam. Okay, and I'll publish this again in the first week of January. The lecture notes are being continuously updated. So in maximum a week, you should have like the full, all the contents until now, but then, so Lorenzo and Julia will go over it to try to integrate it with the tutorials and put also some of the derivations of the tutorials in it. So the final version will be mid-January, but you can already use them for study. And when we upload this final version, we'll write down what the changes are so that you don't have to go through all of it again. Yep. So things that matter for the exam are the exercise. So of course the lectures, but also the exercise from the tutorials, not the ones where we said explicitly, well, this was extra or this was too hard. And also in the book, there's lots of exercises where some of them we did in the lecture, some of them we did in the tutorial, some of them we didn't do at all. So you can go through them and see in the chapters that we treated and see that if you can solve them, right? Okay. So this is, as far as we can tell for now, it will be an in-person written exam. And I think that there's no well, we'll send an email about this in January or February, but I think for now, the guidelines is that there's no flexibility if someone is sick to repeat it later. So if you're sick or if you're, I don't know, you visited family and you don't want to come back to Zurich, remember that there will always be the there'll always be the summer season where you can do the exam instead of now, right? However, it's end of February, so there's hope that things will be a bit better and it will be a bit simpler. Okay, so there's missing lectures. There's about 40 minutes missing of lecture time, but there's a little bit more in terms of content. So I'll upload a total of like 1.5 hours, more or less, of lectures where we'll finish the angular momentum in the hydrogen atom, which I think I cannot finish today. And the other thing is this thing I promised, which is the complete treatment of these heat engines. Okay, so these things will probably not be in the exam, so don't worry, because I know that at least 45 minutes of this will be extra time. Okay, so don't worry about it. I'll upload them for completeness because I think it might be nice for you to see, but it will not be in the exam. Okay, good. So let's start. I'll just summarize what we did in the last lecture. So we talked about spin and how to treat spin in the general case, not just in the qubit case. Right? So we saw that, well, if you have a system, we don't know the dimension yet, but as long as you have some observables that satisfy these commutation relations, right? So the commutator of two of them is the other one with some factor. So we start with this, and then we define these extra operators. So the total spin is just the sum of the squares of the others. And then we define this ladder operator. So the raising operator and the lowering operator, which was Sx plus I or minus I S y. From there, we learned some commutation relations. So namely that this total spin commutes with spins in individual directions, x, y, and z. So which means that they can have common eigenbases. And in particular, we always pick the z as our favorite one. You know, it's the same, like the problem is symmetric among these directions, but we pick one and it was the z as our favorite. And S squared, so we're going to look for simultaneous eigenstates of these two variables. Similarly, we saw that then the commutator of Sz with S plus was S plus with a constant, and with S minus was minus S minus with a constant. And from here, we could define all the eigenstates, right? So we started by taking a subspace, which you call spin S. So these are all the states that are eigenstates of the total spin with this eigenvalue that depends on S. And the reason why we pick this S plus 1 here is that then it will give us a nice relation between M and S, between the eigenvalues of S squared and of Sz. Okay. And the key idea is that since all of our operators commute with this, then acting with them or with these, that's just a sum of those guys, in a state that belongs in this space will keep us inside this space, right? Because look, so take here any linear combination of these operators here, okay? We keep with those or those as well, because they're linear combinations of the others. And we act with it on some state, and this state should belong here, right? Which means that if we apply S squared, then we get this eigenvalue. Okay, but because all of these operators commute with S, if we then apply S squared to the whole thing to try to see if you're still in the same space, then that's the same as, well, it can go inside the linear combination and then it can commute to the other side of Sj, right? But this applied to this state, we know what this is. This is just this eigenvalue, because precisely it was inside this Hilbert space, right? So you get the same eigenvalue, and then what's left? Well, this is a number, so it can go outside, and what's left is the original state that we started with. Huh? So this tells us that applying S squared, so the total spin, to this new state gives us the same eigenvalue as with the original state. Okay. Which means what? That if we are inside this subspace and we can act with this, with all the spin operators, we never leave this subspace. Okay. One example was if you start with a spin 1/2 particle, for example, and we apply all these things inside, we still have a spin 1/2 particle. So it doesn't matter how much we rotate and etc. It doesn't change the total spin. Good. So then we chose the eigenbasis of the Z component as a standard basis. and we just call this eigenstate, the eigenvalues m. We don't know what m was at this point, and you know, this state could depend on something else that is not captured by this operator. So we put this alpha here, which is like some degeneracy. So there could be several states, several eigenstates corresponding to the same eigenvalue. Okay, and then we worked out some math. So we applied these ladder operators to work out that HS, in fact, can be decomposed as a tensor product of two spaces, one that only cares about the spin and one that has the extra stuff. Okay, so that our original state can be written as the state M that depends only here, and some whatever extra there is. And the dimensions of this extra is just the degeneracy of this operator. So it's some dm, which is the same for all m. We don't know what it is, but the dimension of this was s plus 1. Because the other thing we saw was that, so s can take this kind of values, so 1/2, 1, 3/2, 2, 5/2, etc. So multiples of 1/2, positive multiples of 1/2. And m can only go from minus s to s, right, in steps of 1. And so I didn't tell at the time, but these things s and m, sometimes we call them quantum numbers. Okay, so they're just numbers that are important in quantum mechanics because they characterize your states as function of the spin operators. And the other thing we saw is that, well, we didn't explore, and we will not explore in this lecture, is that the ones with kind of half integer spin are called fermions. So fermions most of them have this spin 1/2, and this includes electrons, protons, neutrons, etc. So kind of matter stuff. In things with integer spin, they're called bosons, and this includes, for example, photons are bosons, and carriers of other physical forces. Okay, so like you can think of photons as what carries electromagnetism, light, and there's like forces inside the nucleus of an atom, and the carrier particle of those photons of those forces is also a boson. But we will not get into this. Okay, so this is something, fermions and bosons is something you might get into in quantum mechanics too, for example. Okay. So the next step, after having this subspace and having like an idea of what the dimensions of the subspace are, was to find the explicit form of the operators and states, right? So I said we start with the lowest state with m equals minus s. And then we just apply this operator, the raising operator, to obtain all the other states. And there was a normalization factor, which was this. And this led us to a way of expressing s plus and s minus. So it's just kind of taking this directly here and seeing that the s plus goes from m to m plus 1 and so on. So I think in the tutorial you found the explicit form of these things for a boson, so for a spin 1 particle. It's very good. And now the other thing that we just started to see, and we'll continue today, is how to combine several spin systems. So the idea here is that you bring together several spins. So for example, bring together several electrons, or you bring together an electron and a boson. Or like we'll see later, maybe you have only one particle, but it has 2 degrees of freedom, like think of an electron going around a nucleus. It has its internal spin 1/2, and it also has some orbital angular momentum. Okay, so the total space is like the combination of these 2 spaces. So this is just a tensor product. It's like HS1 tensor, HS2 tensor, etc. Yeah. So you have several systems of spin Sj. And so the first thing you do is to define some global operations, global operators. So we can define the global spin x as just the sum of the spin x on system J, that acts only on system J, and is the identity on the rest. And this similarly for Y and Z. And I think we saw this last time, at least in a simple example, that they satisfy the right commutation relations, right? So these are the operators on the global space, and this is also the operator in the global space. Okay, so this means that we are in a spin situation. So the global space is also a spin space. So this means that we can compute, we can define the total spin, and we can define the ladder operators, just like before. Good. So today, we'll see how to write then the global space, which is the tensor product of these individual spins, as just kind of a direct sum. So if you don't know what this is, don't worry about it. Okay, it's just think of a big Hilbert space that has many subspaces. So it will have subspaces corresponding to different total spin. And then you can think of particles that live inside one of these subspace. Okay, so the example we started seeing last time was 2 spin 1/2 systems. So for example, 2 electrons, and we care only about the spin degree of freedom. So then we can take the basis for the individual spin 1/2 systems. So for example, we'll always write them as S and M. So for each individual electron, we have S being 1/2, and then we have 2 states. M is positive or M is negative, right? So this one we just call up, and this is so that like we can tell right away that it's a system, the state of such a system, and not of the global space. Okay, just use different symbols to be more immediate. Okay, so spin up is the one that has eigenvalue h⁻/2 for Sj, and spin down is the one that has eigenvalue minus h⁻/2. Okay, previously known as, when we were talking about qubits, this was state 0 and this was state 1, right? And the block sphere is the state that's on top and the state that's at the bottom. So then we can have a basis for the global system. So because we have a basis for the individual systems, then the global one could be just like up, 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 down, down, up, down, down. This is exactly the same as saying, well, we have 0, 0, 0, 1, 1, 0, and 1, 1, right? It's exactly the same, just with different symbols. But we'll see. So now we can try to look at what's the action of the global angular momentum Z on each of these states. Okay, so we can do one by hand. So this thing was, like we said, is just the sum of the individual angular momentums acting on individual systems. So Sz on the first system times identity on the rest plus identity on the rest times Sz in the second system acting there. Well, so this acts only here, and it's an eigenstate, so it gets just the eigenvalue h/2, h⁻/2, and the same here acts there and gives this eigenvalue. So we get this, so we get overall h bar and the same state. We can do the same for the others. So not surprisingly, if we apply to down, down, you get minus h⁻/2 minus h⁻/2, so total of minus h bar. If it goes up, down, well, then you get h bar from this one and minus h bar from this one, so you get 0. And down, up, you also get 0. Okay. So now we have 3 values for m. So here m is 1, here m is -1, and here m is 0. Okay. But we know that each of these subspaces for m should have the same dimension, right? This is what we saw before. I'll show you. Yep. Where is it? Yeah, it's here. So we saw that each of these subspaces for S should have just a spin, and then the extra should be the same. But now we have 2 for the same M and only 1 for each of the other 2. So how do we solve this? Well, the solution is that there's actually 2 subspaces, 2 possible values for total spin. So one is going to be total spin 1, where we'll have 3 states. So we'll have value -1, value 0, and value 1. And the other one will have total spin 0, which has only one state in there. Okay. So let's see how this works. And so our goal is to kind of find a map between this individual decomposition of the total space, of the total states, and something in terms of the global S and global M. So for example, here, we know that they're both down, M equals -1, so S is probably 1. Okay. So we'll start with this one because we know that this is kind of the lowest spin one. And what we'll do is we'll apply the S plus. We'll apply the S plus to this, and we'll see what state comes out of it. So we know that when we apply S plus to such a state, we get this normalization factor and then the next state ahead. Okay. So in this case, we'll get this normalization factor. We just replace here the M equals -1 there, from there. And S, we still don't know what S is. Okay, of course, we kind of intuit that S must be 1, but we'll see. And then we'll get this S0. So this is what we're looking for, right? And now, in order to see what this is like, we're going to apply it. We're going to think not of this picture, but of this picture for the initial state. Okay, so we just write it explicitly as being spin down, spin down. And then we can write this operator. We know that it's raising in the first and nothing in the second, plus nothing in the first and raising in the second. Okay. Well, this one only acts in the first one. So we get spin up applied to a minus, and nothing happened here. So still spin down and down, spin going up, S plus applied to this one. Okay. All right. So then, where's this done? Well, we know what this is individually, right? So let's just look at what this is individually for each of these qubits. Well, for each of these qubits, a total spin 1/2. So when we apply it there, so we can go back to the other picture. This is 1/2 minus 1/2. This is the M, and like MJ, and this is SJ. I can even write it here. So this is SJ, this is MJ. And when we apply it, we get this factor again. So here I just replaced the SJ with 1/2 and the MJ with -1/2. Okay. And they turn out to kind of cancel out to 1. And then in the result, we get this state, but this state we defined as being up. So we have H bar up. Okay. So now we just take this result and we apply it here. And what we get, well, we get H bar up, down, plus H bar down, up. And now we know that this thing equals this thing, right? Because we just did it in 2 different ways. Okay. So this was the number on top. And this is what we got at the bottom. So by just, cancel out the H bars and sending this to the other hand, then we get that this state S0 that we're looking for is actually this times a constant. Okay. Now, in order to find out what this constant is, we just need to normalize this state. This state has two terms, so the normalization is going to be 1 over square root of 2. Okay. And what's the s that we can put here such that this number adds up to 2? Well, that's s equals 1, right? Because if you have 1, you have 1 times 1 plus 1, that's 2. Okay. So we found out what s is, and we found out what this S0 is. Sorry, what state with m equals 0 is. So let's see. So now we have two states already. So we know that state with total spin 1 minus 1 was this down, down. And this 1, 0 is this state now, up, down, plus down, up. Now notice that this is an entangled state that we've seen a few times. You've seen, for example, in the teleportation exercise. So this is an entangled state. It's like 0, 1, plus 1, 0 between the two spins. Now we can do this again. So we apply again the S plus operator here and do exactly the same analysis, and we'll end up with the state 1, 1, which, not surprisingly, is the one that has SZ equal 1. So it will end up being this. So now we have three states which correspond to this subspace of spin 1. Okay. And because there's three of them, they're usually called the triplet states. Okay. And this shows up a lot. Okay. Now we're still missing one state, right? Because we know we have a basis of essentially 2 qubits. So there's 4 basis states, and we already have 3, and we need one more. Okay. So it will turn out to be this state here. And the way to find it is to just look for, we need a state that has total m equals 0, s equals 0, and it should be orthogonal to all 3 of these. Okay. So if we do this, we'll find out that the only solution is this state here. So this corresponds to the other subspace, H0. So corresponding to s equals 0, and because there's only one, it's called a singlet. Okay. And whenever there's like 2 electrons standing next to each other, or one's next to each other and then far away, people talk about it a lot about whether it's in triplet or if it's in a singlet state. This shows up everywhere. Okay. So there's some homework that you can do is to show that this is indeed the right state that we're looking for. One way to do it is to show first that it's orthogonal to all of the other states. Okay, so if you do the inner product with each of these states, you get 0. And the other one is to see that if you apply the ladder operators either up or down, you get 0 again. So it's really the only state in this subspace. Okay, so this is, for example, a good question for an exam because it's relatively simple to solve. Good. So what are the conclusions from here? Okay, well, if we have these two spin 1/2 particles coming together, or systems, doesn't need to be particles, then this is equivalent to having a total spin of 0 or a total spin of 1. This has dimension 3, this has dimension 1. And then we saw that there's the triple states and the singlet states. Good. Now, how do we generalize this to the general case where we can have multiple systems coming together? Okay. So the general problem is that we start from this basis, right? Which is just a product of the individual eigenstates of S square and SZ for each subsystem. And you want to find an expression for like the global spin states, right? So the eigenstates of the total global spin and the global Z component of spin, right? Okay, so in the example before, this were this states, and this were these states. This is S and M, which we found out to be of this form, right? So how do we relate these two bases? Well, it's very simple. We just expand the new basis in terms of the original basis, which means what? We take this SM global and we need to write it, SM global, and then plug here an identity, which is just kind of the sum for all M and J of the basis elements, right, in this form. Okay. And this here, this thing here, this is a number, right? And this is kind of the number that we're looking for. Yep. Now, this number, these are called the Clebsch-Gordon coefficients. They depend only on these dimensions of the original system, so on the spins of the original, total spins of the original systems, which means that, there's only so many ways to combine it. You could have spin 1/2 and spin 1. You can have spin 1/2 and spin 3/2. You can have spin 1, 1, 1. You can have 1/2, 1, 3/2. For most reasonable combinations of spins, these things have been computed. So we can, in practice, if you're dealing with such a problem of combining many spins, you can just look up in a table how to do it, what these are. They can be derived via group theory in a very elegant way, but we can also do them by hand once, like Triplet. Okay. So I'll just give you the recipe to do it by hand, which is just a generalization of what we just did. Okay, so the idea is that we know the total dimension, right? It's just the product of the dimensions of the individual spin systems. Okay. And we know that the dimension of each individual spin systems is S+1, or the Sj of system J. Okay, so we know this. The other thing that can be shown as an exercise, maybe I'll put it in the mock exam, is that these coefficients that we're looking for, they are 0 unless this M is the sum of the M's there. Okay. Now, so this is a fact, I'm not proving it here, okay? Now, from getting together these two things, then we know kind of the picture of the M's. So we can see in which ways, in how many ways can we combine these individual MJs to make these M's. So in our case that we saw before, there were -1, -1 gave us a -1. -1 + 1 gave us 2, 0. And 1, 1 gave us 1. So we had a picture like this. Okay. So more generally, you can get a larger picture like that. It's easier as well if you just take two subsystems at a time and don't do them all at once. But from this picture, then you can deduce all the values of S, because then you can count. You can just count like how many M's you have for each S. And then you start like with the lowest one of them all, and you apply the S plus to go up. Okay. Just like we did before, apply the S plus, apply the S plus. And then you get all these states in a column, right? And then you need to go to the next column, so the next value of S. So again, you take the lowest value of M allowed, and you need to look for this orthogonality, and you need to look for a state that if you apply S minus gives you 0, right? So then you use this, you find this state, and then you do again, you find with S plus, you find all the other states and so on. So that's kind of the general recipe. There are more elegant recipes, again, using group theory and representation theory, but we will not get into this. Okay, so this is how you add spins. Now there's a big spin system that we've not talked about, which is angular momentum. So we'll start now, and the rest that we cannot do now, I will record and upload later. So what's angular momentum in classical physics? It's like if you have an object like the Earth moving around something else, some center like the sun, with some distance r from the center of the orbit, and it has some momentum p, so this is the velocity times the mass. then the angular momentum is the cross product of these two. I'll explain what it is in a moment. So in this case, it goes, use this like right-hand rule. If R goes this way and P goes this way, then L goes towards us, which is what this symbol means. Doesn't matter, it's a vector. Why is it important? Because it's a conserved quantity for closed systems. And this means that you can derive lots of physics from it. So the most standard example we know is this ice skating example, where if you're rotating, if you're spinning, then if you close your arms, you spin faster, right? Because there's conservation of angular momentum. And when you close your arms, what you're doing is you're making R smaller. So P needs to be larger, which means your velocity is larger. Okay. But it can be used much more generally, so you can determine like the dynamics of celestial bodies from this kind of conservation laws, even some parts of behavior of black holes, and more prosaic things like spinning tops that you rotate, and so on and so on. It has multiple applications in classical physics. We will not get too deep into this. Okay. So what is this cross product? Essentially, if you have R being the position relative to the center, so some X, Y, and Z, and P being the momentum, so some Px, Py, Pz, then L has this form. And the idea is that this vector will then be orthogonal to the other two. Like here, one goes like this, the other one goes like this, and this one goes outside of the page. All right. So what's the quantum version of this, and why is it important? First, it will be important because it will be a conserved quantity. We'll see this later. And this will be relevant, for example, to compute the orbits of electrons around the nucleus of an atom. Okay. So remember how we talked about 3 dimensions. So if we have a 3-dimension Hilbert space, what this meant was just a tensor product of each of the dimensions. So each line, and line, right? And so we can just define this kind of operator directly from the classical definition. We just write it for now, and then later on we'll see that it is relevant, okay? So what we get is, for each row, we get one operator. Okay, so Lx is going to be ypz minus zpy, which if we put it properly, like each operator in its subsystem, it looks like this. So nothing on the first, y on the second, pz, minus nothing on the first, pz on the second, z. So we have these 3 operators, and what do they have to do with everything we've been seeing so far? Well, the nice thing is that they act as a spin, which means what? If we compute the commutation relations between these two, which we can do, and we can do, we get exactly the same commutation relations as for spin. Okay, so IH bar LZ and the other two. Okay? Since we only have 23 minutes, since we only have 7 minutes, and this is not a difficult calculation, I will skip it, and you can see the lecture notes later. So the only relevant thing to see is that you just write down the expanded versions of each of these operators, and then you'll end up with the only terms that don't commute are kind of look like this, right? So you have, for example, px times y, and then the commutator between z and pz. And we know that the commutator between z and pz is what? Is I h bar times the identity, right? In the same way that the commutator between x and p is I h bar times the identity. So we just plug this here, and the same will happen there, and then this gives us the original, this LZ. Okay. That's kind of how it works. Okay. So if we have this, then we can apply the same recipe as we saw for general spin. So we define these operators, the total angular momentum, the raising, the lowering operators. And now we're looking for simultaneous eigenstates of L square and LZ. Okay. So states of this form: total spin And now, because it's this angular momentum, this was what was previously called S, we'll call L now. And the main reason for this is that later we'll think of particles that have both S and M and L, and like an electron that has some internal spin and then some angular momentum, and you don't want to use the same letter. That's the only reason. Okay, good. So now we are looking for this state, these eigenstates that behave like this, right? So the action of L square is going to be the same eigenvector as we saw before, the same eigenvalue as we saw before, times the state again, and the action of Lz is going to be this. Now, these states are states in 3 dimensions, right? So they live in this composed Hilbert space. So more explicitly, well, we can expand them in some basis for this composed Hilbert space. And what we get here is going to be a wave function that depends on L and M, and as arguments X, Y, and Z. Okay? And what we're looking for in order to work out the physics of this kind of settings is to look for what's the form of this eigenstates. Okay, just like before, we saw that for combining 2 spins, the form of these things was this spin up, spin down, plus down, up, right? So we're looking for these objects here, these wave functions. Okay, so what would the procedure normally look like? Well, first we need to find the explicit form of these operators, which you can do. For example, we know that the momentum in some direction k, we saw this a few times, acting on the wave function, it acts like this, I h bar, and then the derivative in order to this coordinate. So k could be x, y, or z, for example. And therefore, we can write, for example, Lz, well, it was this thing. So now we know how it acts on the wave function. So it maps the wave function to what I h bar, which comes from there, and then we have x and derivative in order to y minus derivative in order to x, y. Check. Is that true? Or is it? Sorry, give me a second. I think it doesn't need to be. Yeah, it doesn't need to be on this side. Sorry. Right, there we go. Okay, yeah, because they act on different states, on different spaces, so it can be written like this. Good. Okay, so then we'd have this. So then we just need to find the eigenvalues and the lowest eigenstate, and then apply this ladder operator to find all the eigenstates, right? So what's the problem of this? These are all this angular momentum have to do with rotations, right? We saw before it studies problems like the orbit of a planet. Okay, in this case, a quantum planet, like an electron. Which means that if you try to describe this orbit in terms of our usual coordinates, x and y, this is going to become extremely clunky, right? Because x goes up a little bit and then down and then up again, and the same for y. It's not a very easy function. But if you express it in polar coordinates, where you only care, for example, about this and this, then it's very easy. So for a circular orbit, we know that r does not change, and this theta just changes kind of linearly in time. So in the 3D case, it's going to be even more complicated to work in these Cartesian coordinates of x, y, z. So it's much easier to work in spherical coordinates, okay, which are what? They are exactly the same as we saw in the block sphere. So this is your usual x. Sorry, it should be an x, y, z, and then the coordinates we actually want to work on are r, theta, and some angle phi here. Okay. So then the problem is going to be to express a wave function of a given time it's much easier to work not with this wave function, but wave function in terms of these coordinates, okay, where the arguments are going to be some psi of r, theta, and phi. Okay. So what is next? What we have to do next is to try to find out how we transform from these coordinates to these coordinates. Okay. And this is something that's going to be a little bit elaborate, so I'll do this in the video that I'll upload next. But the procedure that we're trying to find here is really try to find what are the eigenstates of angular momentum. Okay, and then later on we'll combine the eigenstates of angular momentum with the ones of spin to try to solve the problem of the hydrogen atom, which is one single electron orbiting a nucleus. Okay, and we already have all the ingredients, I think. So next thing now is this kind of grind work, and this is what I'll upload later. Okay, so we'll stop here for now, and I hope to upload this lecture this week. So today or tomorrow. All right then, see you next year, I think, and happy holidays.